welcome to PETRA's second of two webinars on digital twin models on geometallurgical and materials handling indices, closing the gap between plan versus actual performance. My name is Leon Morgan. I'm the head of partnerships at PETRA, and I'll be your host for the next hour. Really good to see so many people here from across the world. Actually, this session that was targeted for targeted for North and South America. We've still got some people from Brisbane there. We've got some people all over the place. And we're really happy to see it. The aim of all these webinars in this series was to keep people connected and informed and keep talking about innovation and the flow of information going through while everyone's stuck at home. And I think we're doing that quite well, personally. I'm really excited about it. Today, you'll see a brief case study on PETRA's Geomet digital twin models, with the bulk of the hour spent on a Q&A session between our guests and panel. I imagine after the last few weeks, we're all pretty familiar with Zoom and every other conferencing system out there right now. But I will ask a few things. If everyone could stay on mute for us, that'd be great. You can leave your videos up if you like. There will be recorded, mind you. We don't put everything up online though. If you don't want that up, anything up there, just let us know. We'll make sure that happens. So that's general housekeeping. So yeah, well, you didn't come here to listen to me too much, so I thought I'd start with some introductions, which would be nice. So firstly, we've got Professor Peter Dowd. Peter has more than 40 years experience in academic research, teaching, administration and consulting in mining. Much of this work has been modelling and estimation of ore bodies, often very complex geology settings. Also the generation of three-dimensional ore body models as the basis of optimal mine design and scheduling, and the qualification of geological and technical risk association within resource extraction, just to name a few. And I'm amazed I didn't fall over that at 4 a.m. Peter has been cited as one of Australia's 100 most influential engineers by the Institute of Engineers Australia, and is the director of the Australian Research Council Industrial Transformation Training Centre for Integrated Operations and Complex Resources. We're really happy to have Peter join us. We've had some amazing discussions already, and I'm hoping to continue that this morning. Secondly, we have Orlando Varas. Orlando is with 25 years in the mining industry, over I think 3 continents from looking at his CV, but I might have missed 1 or 2 there. He started his career in Chile and working through North America and here in Australia. When I read through Orlando's brief, I feel like I'm probably not going to do him justice here, but I'll let him speak for himself when the time comes. Orlando was project director on the pre-feasibility studies for Mount Isa, consisting of 2 mines here in Australia, and is currently the lead of resource development planning at Anglo America. Developing holistic resource development planning studies with strategies that maximize value across the value chain, specifically delivering strategic mining operations for individual assets to create an integrated work of solutions across all disciplinary streams, which I think fits very well with what people talk about the Industry Transformation Training Centre. We're excited to have you along, Orlando, and I hope we can do some more chatting after this as well. Lastly, we have Dr. Penny Stewart. Penny is a mining engineer and founder and CEO of PETRA. Penny worked on mine sites for 5 years before obtaining a Queensland First Class Mines Manager Certificate of Competency. It was during her time working in underground and open pit mines of WA here that she learned how geological uncertainties affects our ability to mine to plan. This experience led her to study the mechanical behaviour of rocks as part of her PhD studies at UQ's Mineral Research Centre, where she developed her statistical analysis and modelling expertise at a time when most people were interested in applying numerical modelling. In 2015, Penny founded PETRA with the hypothesis that the engineering behaviour of rock throughout a mine is best estimated by feeding back hundreds of millions of tonnes of actual mine performance data into engineering models and optimizations. 5 years later, PETRA's flagship product MAXTA, which we'll show you a little bit of in a moment, does exactly that. I'm pretty proud of it too. So please join me in thanking the group here this morning. I assume you're clapping very eagerly. So with that, I might pass the penny to a quick presentation this morning.
Okay, thank you, Leon. Okay, I've just got a 10-minute presentation on Geomet and how we do our geometallurgy modelling. It's mainly case studies, actually, just to show the sorts of things that it's used for. But the main purpose of MAXTAGeomet is to provide input or accurate input for mine planning and mine optimisation. So the way that this is able to be achieved is effectively through remining the ore body in a virtual way. So that means that you can, we remine it using the data, we use the fleet management data, we use the block model, and we track that ore through to the plant. And that means that we can then feed back how that particular ore behaves in the plant back into mine planning. And that's done through the block model. So you have, at the end of the day, a block-by-block prediction of how that particular type of ore is going to behave when it hits downstream processes. So those downstream processes can include material handling processes like throughput on crushers or throughput on other parts of the plant, or it can include the recovery, it can include other aspects like how a particular ore is going to behave in an autoclave, for example. Typically, we'd be feeding back tens to millions of tonnes of ore, which would come over between 1 and, say, 4 years of mining history. So you may have heard the term digital twin in relation to this approach to geometallurgy. What we're meaning there is that we're building a model that integrates the data with the real world. So it's real world data, which means that the model is linked. So we've got, what we're doing here is we're integrating the data from the real world and building a model from that real world data to build a digital twin model. It is in the mine a offline digital twin, so that means that we're not connecting in real time into those data sources except through the updated block model. So whenever you update the block model with new geological input, then you can upload that block model and get a new block model back, but it's not connected in real time. In contrast, in the processing plant, we get we do have live connections, and the digital twin is fully live and it can learn and retrain using real-time data streams. We are currently in the process of working with one of our customers to build, we built the architecture for it, but it's just a matter of now going ahead and then deciding when they want to do that. Okay, so why would you want to have a digital twin? In the case of geometallurgy, the reason why is that you're looking to be able to get better estimates and predictions of how the ore is going to behave downstream. So that can include, as I said before, crushers, throughput, yield, those sorts of things. But the other reason that you might is you want to ask what if scenarios. So that's the simulation side of a digital twin. And we have the same type of model. It's the same sort of machine learning model, but it's asking a what if question. So we had a webinar a couple of weeks ago, and it was all about drill and blast. So in the case of the drill and blast digital twin, we're asking the questions, if I change the burden, if I change the spacing, what effect will that have downstream? Okay, so that's the simulation side of the digital twin. The final part is the optimisation, and it's not necessarily an essential part of a digital twin. In our case, it's optional, so you can then, what that means is you can learn from the historical data how they got their best historical performance. So how did you get your best crusher throughput? How did you get your best drill and blast outcome? And you can learn that by running an optimization over the model. Okay, so I've got some case studies now to go forward with. We've got the case study from Panos Banasai Silver Gold Mine in Laos, and is based upon about 10 million tonnes of ore. It's a small gold mine, and this case study was first presented at the AusIMM's Complex Ore Body Conference in Brisbane in 2018 by James Carpenter. James was with us yesterday. He's working in Egypt at the moment, so he couldn't join this particular call, but he was able to talk last night, and if you're interested in his comments on this case study, we'll make that available to you as well. So this is the Unicycle silver operation. It's an open pit mine. It started in 2012. We integrated about 10 million tonnes of ore into MAXTA by remining that ore, and approximately 5.12 gigabytes of data were ingested, including the fleet management data and also the Pi historian data, which in this case we were modelling the recovery. So they had a historical issue with being able to predict their recovery, and sometimes the recoveries they were getting in the plant were down to 50% recovery. And even though they had put a lot of time and effort into traditional Geomet testing program, and James spoke about this yesterday, that even though they had done that and they'd done all those tests and built a Geomet model, they weren't able to forward predict where that low recovery area was going to come from. And so this is where they decided they would try a different approach, which was to use historical data to remine it with us. There's a video now, which I hope that you can see, showing the operation. We've just flown over the top of the processing plant. You can see the ROM pad down there. And shortly it's going to switch over to a mine planning view. And what you'll see is some red and pink blocks. They're the ones that when we remined the data and put the machine learning model back into the block model, they're the blocks that we were able to predict had issues with recovery. And the site, according to the site, they agreed very well with the areas that they had historically had issue with recovery. And so they decided to move forward and use this in their life of mine planning. So here's a image from their presentation that James gave at the Complex Ore Body Conference. And you can see here that what we were doing was predicting high tails grade as a proxy for low recovery. And you can see here that they were then using it through life of mine to identify where they should, which areas of the pit were actually ore and which areas aren't ore because the recoveries were too low. And that enabled them to update their mine scheduling and their mine optimization. The second case study I have for you today is from an open pit mine. And they had an issue with highly variable throughput for their mills. It's not an uncommon problem. They just had some ore types that were particularly problematic, particularly hard, and they also had some areas of pit which were quite amenable, quite reasonable process mill grinding properties. And so their opportunity was to blend. If they knew where those particular ores were coming from in the pit, they had an opportunity to blend. So the opportunity here was to smooth out their performance of their mills. And what you can see here is the block model showing the different the colours basically mean where the red is the low throughput and the green is the higher throughput, so the cooler colours. And so they were able to identify in the pit areas that they could expect they would have lower throughput in the plant, and then work to blend that with other ores to improve overall mill throughput performance. So when we get to this point and you've got the predictions back in the block model, one of the things that first people start thinking about is what is this? What is in the model, and how are where are these predictions coming from? Because it is quite a different approach to some of the empirical modelling methods that are used. So what we're doing effectively is treating all of the geological data that is in the block model. So it could be hundreds of variables that may be there, and we treat them all equally. So we don't go into it with a hypothesis testing approach, which you would normally use in a statistical model building approach. Everything is treated equally and then automatically analysed. So that will include the Geomet testing as well. So if the Geomet testing results are in the block model, then they can also be leveraged and used and valued within this approach. So it's not uncommon. This particular mine doesn't have much Geomet testing hadn't done a huge program, so their geomet testing didn't come up particularly high in their features. So what you can see on the right-hand side is a range from highest significance predictor down at the bottom to lowest significance predictor. And you can see that the ones which have a red value on the right-hand side, they're pushing the throughput to be higher. And the ones that have a red value on the left-hand side are pushing the predictions to be lower. So it's this combination of all of those features. Particularly, we find the geomet is particularly, not the geomet, we find that geochemistry has quite a strong impact, and you can see some of those geochemistry properties up the top there. The purple ones that you can see, some of them don't have strong blue and red, and they are the ones which are the interacting features. So some of, like this one here, the magnesium, what that means is sometimes magnesium causes the throughput to be high, and sometimes it causes it to go lower. And it's some of these interacting features that you won't get in a statistical model, because statistical models have consistent or constant correlation coefficients that push the model in one direction and can't push it back the other way. So that's my case studies. I'll now stop sharing and hand it back over to Leon. Thanks, Leon.
Thank you, Penny. I did get a few messages around Penny's audio. I might ask Penny if you've got your hands free, your headset, if you want to be on that, just because it might clear up a little bit trying to get into that, if you don't mind. Hoping that works, which is good. So to the Q&A session. Great. So I think a few people have found the chat function, which is down the bottom. If I don't mind, if you ask, if you grab the chat box down the bottom, you can open that up. It's in the middle. Wave your mouse on the screen if you need to find it. If you want to ask questions through that to everyone or privately to myself, we'll address them when we can. I've got a few questions here to get us started off, which should be fun. But I thought I'd ask the team here if you have any initial thoughts or anything you want to just jump on around the topic itself this morning. I might start with you, Peter. Is there anything you want to sort of just jump on?
Nothing particular, except maybe I might explain my interest in this and the relationship with PETRA. This new training centre is, as I said earlier, an attempt to look at integrated operations for complex resources. So in this case, the complex resources are IOCG-type deposits. It has two major end users, BHP and Oz Minerals, and has around 20 other industry partners, including PETRA data science. The aim is to look at the entire operation as an interdisciplinary construct and not break it up into individual components and individually optimize those components. So everything that Penny presented then, in a general sense, is relevant to what we're trying to do. The focus on geometallurgy in this particular presentation today is very useful, because it's, for me, it's one of the missing elements. It's one of the things that we need to know, but we're not prepared to invest the money to find out about it. I generally find in operations where I've been involved with Geomet that the data are very, very sparse compared to, say, grade data or any other data for that matter. Once you have those data, they're not representative of the entire operation because they're so sparse. And the other issue is that they do not have nice properties. They're not additives, so taking averages of them or using techniques like kriging to estimate them simply don't work. Once you collect the data, though, then you must integrate it with everything else. So it's pointless looking at geometallurgical data without looking at grade and other sorts of variables. So that is a fundamental issue. And I'm quite optimistic of machine learning type approaches that Penny just mentioned of addressing this sort of problem.
Fantastic, Peter. And Orlando, any opening thoughts from you, my friend? You're on mute, mate. I'll get you off it. It's all right, I got you.
Yeah, sorry. Well, I'm very passionate about finding value and optimizing value, and traditionally, in that sense, most part of the value was just looking in the mine, and I think everybody now is squeezing the mine as much as we can, and the next stage is in the processing and downstream to the mine, and the world that 20% is it looking in that direction. So yeah, I'm happy to see that, and yeah, I'm very encouraged to promote that sort of approaches.
Yeah, perfect. So I've got a question here for you, Orlando, to start things off, mate. I thought I might ask if you could give a good high-level overlook of the value and the impact that geomodeling like this has on the entire process.
Oh, well, let's say, I mean, we always, all the people who work behind a my plan or try to optimize a business plan of for my company is we're trying to grow. We're trying to grow to try to make even more production. At the very end, we try to produce more cash flow. And traditionally speaking, most part, as I mentioned before, was done optimizing the cutoff rate in the mine. So traditionally more mine, export high grade ore, and because that we send better production to the marketing. However, I mean, with the pass of the time, I mean, the grade is going down, and we have no more option to keep. I mean, or if we keep applying that approaches, at the very end, the results have a limited capacity. So, and traditionally, when we find that point, so the typical response was, okay, expand, make the process facility bigger. And that was working for probably 20 years, or maybe more, but the point is now it's not only capital very intensive, it's also difficult in terms of permitting, so it's taking too much time to do that. So the most economic approach now is just, okay, what happens if we optimize the rest of the business stream? And there's a lot of value just increasing our ore body knowledge in terms of geometallurgical behavior, and how we integrate that behavior across all the value chain. And in our experience in Anglo American, when we do that, which is not easy, by the way, you can achieve 5 to 10%, maybe more, depending on the response of the ore body, how good is well defined your ore body. Unfortunately, the geometallurgical is like the poor brother of the family, because we spend all the money drilling and trying to understand the geology in terms of grade and other quality things. However, the metallurgical component has been very, very limited budget all the time, and because the testing takes so much, and particularly because modeling in an integrated fashion all the behavior across the value stream is take a bit longer compared with the statistical modeling of the grade, for example. It's there's a lot of barrier to keep doing that, and that effort has been sometimes pushing or pushbacking, which is really not the best way, in my opinion, to do that. So, but I have to say, in my experience, you can find between 5 to 10% easily if you do that.
Yeah, fantastic. I think that sort of leads into a good question I've got here around what do we need to improve? What are the challenges that are existing today for us to get to that point where we can start seeing those sort of impacts? Orlando.
Well, essentially, we need to understand better the metallurgical behavior of our body, and for that we need more sample, more testing. We need to identify what different ore types respond differently in different situations, and the different commodity prices, and for that we require a lot of modeling, and that takes time and a budget, but if you compare the budget with doing an expansion, is very minimum, So what I want to say, the value add by improving the geometallurgical knowledge is for far the most MPV efficient way to spend the money.
So speaking of money, how does that then inflect investment decisions that you or the company will be making as well? Are you able to use geological information to make better investment decisions?
Absolutely, absolutely. We last we did a portfolio review in Anglo American, and we found for all the opportunities about 11%, 10-11% was just for asset optimization, and it was a huge value across the whole portfolio, and that was just because doing this in more smart, applying, and it was under very limited additional information on geometallurgical. You can imagine how much we can gain if we just increase the value or increase the information that would support our geometallurgical model.
And on that to you, Peter, as well. How do you see things, projects like your training centre as well, having impacts on other aspects of the mine by pulling in all, like you've said, with all the looking at it as one whole challenge rather than little ones within itself? How do you see the impact moving forward for companies like Anglo America or the partners that you have?
Well, it's more than simply looking at this as something that is integrated. If you look at the people like myself, for example, that work in these areas, they come from one specific discipline, so mining engineering, geology, and so on. In this, we're bringing in mining engineers, mechanical engineers, electrical engineers, mathematicians, computer scientists, and a whole range of others, geology and so on. Every PhD student, there will be 16 PhD student projects and 3 postdoctoral researcher projects. Instead of having them located in individual departments or schools, they'll all be located together. So they will work together in a single large operating room where they will feed across the disciplines and look at a truly interdisciplinary approach to things. So it's not simply a matter of solving individually a component of the problem. It's bringing interdisciplinary expertise to solve that problem. And we deliberately use interdisciplinary rather than multidisciplinary. Everybody's reasonably good at multidisciplinary by bringing people in and giving them their component parts. So this is to train what we've called the next generation of scientists and engineers to work in complex resource estimation and modeling. So I think, to cut a long story short, I suppose it's really about interdisciplinary integration to solve an interdisciplinary problem.
Fantastic. So speaking on that, and feel free to jump in, either of you or Penny, what do you see as the greater impacts of connecting the geology to the rest of the process like we're talking about? Where else do we see impacts? Is it we're talking about metallurgy obviously here, but what's the greater flow-on effect from that as well?
Well, the integration will take place across everything. So right from the beginning, the way in which you plan a drilling program, the way in which you extract the ore, the tracking of that ore through the entire system. And it's based on, I was going to say ubiquitous sensing, but that's a bit of a challenge. But certainly a lot of the projects are based on developing new sensors or expanding what current sensors do. And the concept is to use the IIoT plus ubiquitous sensing to integrate processes throughout the entire chain. So if we want to know, for example, I think Penny referred to something like this in the second project you were talking about. It's pointless trying to optimize some aspect of the concentration plant or the crushing plant or anything else in the system without knowing what is in the system coming into it and what is coming out of it. So it's that whole integration of sensors with standard type data, call it hard data as opposed to sense data, and carrying that through the whole value chain.
I'll get back to sensors, but on that, what you're talking about there, so we currently do test, obviously we do test the geology and its effect on the plant to a scale. What do you see as the biggest differences between current techniques or past techniques and techniques like we saw just earlier, we're using machine learning and larger amounts of data?
I suppose machine learning offers something that standard statistical or geostatistical techniques can't do when your variables are not additive. So most of everything we measure directly is based on a specific volume, and it's currently the most common form of it is to measure something directly, say by assay. That takes time. And if you want an answer in real time, you really got to be able to find the data in real time. And that's the advantage of sensing. Having sensed it, you haven't solved all the problems. The problem is, if I measure something directly, say on a core grade, I know the volume to which the grade what the grade is for that particular volume. If I send a sense signal into the earth or conveyor belt or any other aspect of it, I don't know exactly what volume is being measured, so I need some way of calibrating that so that I can integrate it with other data. So I suppose the quick answer to your question is collect data in real time and make real-time decisions.
I saw you nodding there, Orlando. Do you have anything to add on that one?
It's about integration that Peter mentioned. I think, again, traditionally, mine engineers will optimize my plan in the sense of how much metal or product we can produce. Then metallurgical produce optimizing something about that, and then marketing and financial guy produce another sort of optimization for that. And but those were not related, essentially in the past. And I think now we are looking for what we call value-based planning, which is integrate everything, and that forced us, or at least the people who are doing the mine planning, to understand everything. It's not only my planning, it's not only mining, it's just how the other activities downstream behave. So what means that we need to fight for every penny in the cash flow chain. So we need to discuss with the metallurgical why this throughput is not higher or lower, or why it's responding differently. Actually, we fight with the financial guy why with the cost modeling is not reflected in the cash flow at the end. Because we need to be very well calibrated. So, and that is forcing, obviously we are moving people from outside of the comfort zone because they need to expand their way of thinking, because the most important is value at the end, not production. And sometimes you find don't produce more cash flow. Just because you make a wrong blending or a wrong decision, and sometimes high grade is harder and lower throughput and lower recovery for any other reason, or have more deleterious element which contaminate the final product, which produce more penalty at the end in the marketing. So when you combine all these things, in an integrated fashion, it is obviously you produce the best outcome. And what Peter say, unfortunately, many of the value drivers are not additive attributes. So that means it's not easy just to make a weighting average, calculation. You have to simulate and make calculation in an iterative way to see how they each respond to the different blending. Let's say harness. Harness is a issue find, and a soft rock is you combine equally part with a hard rock. It doesn't mean you have half of medium rock. And that means force you to make a different type of simulation of that blending, how perform into the whole stream value.
Fantastic. Penny, do you have any thoughts there as well?
Yeah, I think it's a good point that both Peter and Orlando have mentioned is this non-additivity and the benefits you can get from machine learning when you look at the combinations of ore as they arrive at different points along the value chain. So with machine learning, what you can do is you can get the blend of ore that it's seeing at that point, and the machine learning algorithm will take into account that non-additivity, and that's quite a powerful thing, because it means that a good example that Orlando gave is you can have a very high throughput ore and you can have a very low throughput ore. And if you average the two throughputs, you don't actually get that, tons weighting averaging. You may not get the tons weighted average. It's not how it works. And so having the ability to combine those ores and predict how they're going to behave when they're combined in a non-additive way is very, very useful for mine value chain optimization. And we do have customers who are doing that now. So how that's done is we take the processing approach. So we have MAXTA process, which we run in the processing plant, and we push that back into the mine so that when the different ores combine in the mine, we run the machine learning algorithm at that point in the value chain rather than just using the tons weighted averaging. And the benefit is that you can do geometallurgy on non-additive features. And both Peter and Orlando have raised that, and I'd just like to emphasise just what a breakthrough that is for mining. I totally agree.
Fantastic. Good conversation early in the morning, team. I'm loving it. I might stick with you.
Can I just add, Leon? I think that's one of the that is one of the most transformational aspects of all of this work for mining companies, because in my entire career, all I've ever done is mass weighted averages, and it doesn't always, it's the best proxy, it's the best estimate we've had, but it doesn't always work out that that's what happens when it goes through the plant.
Mm.
Yeah.
Yeah, thank you.
Thanks, Carmen.
Thanks, Carmen. I might stick with you, Penny. Something came up yesterday in our thing, which I think is a really decent point to talk about, is sensors. Peter mentioned IoT and data collection. The industry's been collecting data for years and years and years, and a lot of it sits and collects dust. There is always a new fancy sensor. There is always another way to collect data. Penny, do you think that what data we have available today is enough? Do you think that we need to create more to get good results? And how do you see this evolving?
Okay, thanks, Leon. Look, it's a really good question. In our experience, we're getting, obviously we've been doing this now for over 4 years, and we do believe that you can get a lot of value from the existing data. Okay, when you go to build a machine learning model, you don't have to use every record in the data set. So a lot of the algorithms that you apply, it's all about assessing and validating the data so that when you finally build up a record of what's arriving at different points in the value chain, you build the model on the data that you have confidence in. So there's all types of terminology around that, like valorization and veracity, all of that side of it. And then once you build the model on that good data, you can get some very powerful outcomes. But is that enough? Can we improve? I think that the work that the ARC through the PhD students with Peter Dowd's group, that they're going to come up with some new methods that will provide more fidelity in that data and more, meaning you'll get more precise information on a tighter time frame. That's going to be useful for when digital twins become more and more real time, especially in the mining side of things. So at the plant side, we have a lot of data that collects through systems like Pi, and what that means is although they may not be directly measuring something, they'll be really good proxies for things. So in the processing plant, I think we've actually got some really good proxy data that we're already getting through the thousands of tags that come off in those Pi systems. But in the mine, there is less of that sort of data available, and I do think we will get a new level of richness from some of these new systems. But do we need them now? Do we have to have them? No, I don't think we have to have them. It's just that to create value right now, but it will certainly enhance the benefits as we move to a high fidelity digital twin modelling.
Fantastic. Do you guys have anything to add on data there, gents?
No, I've got nothing to add.
Good. Glad to hear that. It's always nice to get a nice clean point off there. So we actually had some good questions for you, Penny, here on the model inputs and so forth as well. So just from David here, wants to ask us to talk more about model inputs for what you've shown in those case studies, which are in test work and direct from Geochem themselves. So do you have any comments there?
Yeah, look, we basically take everything that is in the block model, and we've also in the past integrated in drill hole information as well. So it doesn't have to be in the block model. We can also take drill hole, downhole data that may also be provided and ingest that too. But we don't make a decision and say we're going to use this test work or this test work feature and ignore something else. It's done very objectively. So everything is actually analysed, treated equally. There's no stepwise model building that people who've built statistical models, you go through a process of hypothesis testing as you build the model to work out what your important predictors are, and there's a bit of a bias and subjectivity in that process itself. But with machine learning, you don't have to do that. You can treat everything equally, and it'll work out what is significant. And then based upon one of the inputs you may make is we don't want to spend all this money on some particular program that you've been doing in the past, and so you may find a proxy for that in your machine learning model and decide not to keep doing that particular work in the future, and so you might choose some other parameter to use in the model. So sometimes there might be human input into saying, look, we really don't need, we've got a really good correlation with something else, and we really don't need to keep doing that and collecting that information. So there are some opportunities like that where you can find those highly correlated features, but most of the customers we work with aren't really changing the data that they collect off the basis of this, but there have been those questions raised in the past. So does that answer that question?
I believe so. I think that leads into the next one here as well, around making decisions on what proportions for blending to increase that throughput as well. So I might pass to you, Penny, and also ask Orlando as well around decision-making process aligning to these types of models.
Okay. I'll talk about it just very quickly then. There's two ways of doing it. The case study that I showed in that example, they were just using a tons weighted average scheduling approach, the traditional we're going to blend a bit of this and a bit of that, and we're going to average it out and hope that we get a smoother performance, and having smoother ore characteristics going through the plant, we should get an uplift, okay? That is a legitimate approach, and you can easily get 5 or 10% uplift just by providing a more even throughput to the plant. But that's not optimizing the blend. The next level is, which I referred to briefly before, which is that MAXTA process approach. That's when you actually look at how the different blends, when they get brought together, how they're going to behave using the machine learning model as it arrives at the plant. And that particular operation has now moved to that point. So the next phase of work we're doing with them is to apply MAXTA process as the ore arrives at the plant. And that is more optimization of the blending. So just to make that different.
Do you have anything to add there, Orlando, on
question?
Decision making? Yes.
Well, it's not easy, but it's not as much difficult. I mean, it's just when you want to optimize the mill throughput, well, you must put that the objective is in that way. For example, traditionally in copper mine, we use a percentage of copper to drive the value, or to drive the ranking, how we decide this is going first, this is going second in the queue of going into the process facility. I think the key component now change the ranking in terms of value per mill hour, or value whatever it is that constrain your process facility. Traditionally it was moving from metal to mill hour. Now, for example, in Chile, we have some constraint in terms of water. Probably water is the key driver rather than mill hour, than energy, and probably is valued by cubic meter of water. So you must rank the ore in what is your value, your key value driver, what is constrain your process. And that, in that way, if you rank the ore in that way, you will secure the best cash flow in every minute. So I always say, we have a party here, and you have to decide who have the high value ticket.
Yeah.
You know? It's not the tall, the tiniest. It's just who have the high value ticket, and the high value ticket going first to the party.
That's good. I mean, what I'd like to talk about now, if you don't mind, is license to operate. So we spoke about this yesterday in our webinar then as well. And it was a really interesting point that was made around license to operate isn't just around safety anymore. It's around environmental and energy use.
Yeah, absolutely.
As we progress into this new aligning geology to other decisions, how is this going to affect license to operate and other aspects from that end?
Interesting, because obviously everybody wants to grow, but usually growing it's mean bringing more energy consumption, more water consumption, more impacting area. So that's mean we can probably do traditional expansion. We can certainly add more value for the shareholder, but the community who provide us the license to operate is not going to be happy at all, because we are, in many sense, we are not going in the right direction of being more sustainable. So the only way is just to include those sustainable goals into the mine planning process or into the objective of the optimization of the asset. So that means in your model, you need to be very well know how much is the water consumption per ton, or how much energy is every single piece of block you send to the mill is demanding, and obviously put on a cap or on a limit in that production. And that probably the answer is, we need to produce less to satisfy those goals. And that means, it's less value to the shareholder. It's a problem here. So then we need to find a way to how we back again to be a high efficient and high productivity respecting those goals. And that probably needs investment. So we need to find new techniques to try to do the same metal product per period with less consumption. So we're in a technological challenge here, because it's quite difficult to satisfy those sustainable goals without with the same type of process that we have so far. And I think any step and any initiative moving forward in that direction is gonna drive the mining company value in the future.
Yeah, fantastic. That's a really, really good point. Orlando, thank you. Peter, do you have anything to add on license to operate? We had some good discussion about that yesterday as well.
Yeah, I suppose the more detail you know about what you're extracting and processing, the more decisions you can make. So why pass large parcels of ore through a processing plant when 20% of them are not going to yield any profitable value? So crushing and grinding are expensive. They're environmentally damaging. Producing waste and getting rid of the waste is environmentally damaging as well. So the more you know about it, and the greater the detail you know about it, and that's achieved by ubiquitous or near ubiquitous sensing of things, the more you can divert sub-economic material from being passed through the value chain. The more you do that, you must be reducing the environmental footprint of the operation. So that is a very straightforward, simple approach to it. Of course, the whole problem is much wider than that, as Orlando just said. But if you could do just this and save maybe 5% of what is unnecessarily being processed through a system, you've contributed to not environmental sustainability per se, but you've reduced the environmental impact of what you're doing.
Yeah, great point. Penny, do you have anything to add there?
Yeah, I agree with both Peter and Orlando's comments. I probably add one more thing, and that is that when you go through that process of putting estimates of specific energy, which, how much energy per tonne and how much water per tonne, and you put that into the process of mine planning or resource engineering, mine optimisation, what that means is you end up selecting blocks that are more sustainable. And so over the life of the mine, it will just organically choose blocks that have better sustainable performance. So I really like the idea of building more and more of these environmental metrics or not environmental, but sustainability metrics into the block model. So specific energy, for example, if you can put accurate specific energy estimates into the block model, then you get more accurate estimates of actual energy consumption. And so that then becomes, that is a cost, and that will then drive the optimization organically. You don't have to force sustainability. It becomes an economic imperative to get it right. And it's the same thing with water as well. Like if you can get that right as well and incorporate that into the mine optimization process, again, you'll be making the right decisions about which is the best ore to mine and which ore you shouldn't necessarily mine. So it's a bit about, Orlando talked about it, and so did Peter, selectivity in what you mine and processing the ore that is going to give you the not just the highest grade. So we've almost always used grade as the main driver of value, and we haven't put a lot of effort into quantifying the cost of different ore types in terms of energy consumption. When you start doing that, the other benefit you get is that you put pressure back onto the engineering design team to evaluate alternative methods of comminution. So the problem we have in mining at the moment is people just want to put SAG mills and ball mills in everywhere because they're known and their properties are well known. But there are other alternative comminution methods that often don't get a look in because we don't realise what the true cost of those that equipment is, because we're not differentiating for the different ore types. So when you start differentiating for different specific energy, then you can start looking at things like thermal. There's things like thermal. There's some research going into how you can use thermal pulsing or something to reduce the strength of the rock to make it more efficient to grind. There's dry grinding. There's HPGRs. There's different types of comminution technology that often doesn't get the attention that it should because there's just not the understanding of the specific energy of the different rock types.
Yeah, perfect. I think that leads into Julio's question here around using geochemistry and use for metallurgical recovery as well. You might see that question there, Penny. Do you have any thoughts on that?
Oh yeah, I saw that question. We do geochemistry. If it's in the block model, we will use it.
Yeah, perfect. I've got a good question here from Dave as well around the model deal with areas of mine that be quite different from the data set itself. Perhaps a different geology or something not previously fed into the data set. I think it's a really important point to cover.
Yeah, thanks, David. That's a good question. One of the advantages of a machine learning model is that even if you've only got a small percentage of your total data set that represents a particular geological characteristics, it doesn't get biased by the amount of that. So if you have as long as you've got enough, like you still have to have enough records in the database. So typically we might have hundreds of thousands of records in the training data set. And if we have maybe we would normally want to have at least a couple of thousand records related to particular geology. And what that means is when you mine an adjacent ore body that may have a whole lot more of that, so you might have another pit that you're about to start, it's located 500 metres away and it's got a lot of that ore, you can actually use that, even though it's a small amount, it will still predict it just as well as though it had been 50% of the original ore body. And that's one of another advantage of machine learning is it's not biased by the amount of data that you put into it. So each what do you call it? Yeah, characteristic geology. If it's there in the original training data, you can then use that learning from that pit, even if it was only 5% of the previous pit, and you can use that at the next pit where it might be 50% of the ore body. So that's another interesting advantage that you get as well.
So that actually brings up a good point. You've alluded to, obviously, well, you showed, models on throughput and recovery, and you've alluded to other areas like fill and blast. Do you just want to cover off on a few different areas that this same sort of techniques can be used on for optimization and simulation?
Yeah, look, we've got big rate models as well. We've got a specific energy one we're working with at the moment. Just for everyone's benefit, the specific energy models, we're not charging license fees on those because we really want to see industry uptake of the specific energy models. We have done models for like how it's going to respond in the autoclave in terms of the temperatures that will be generated with tailings grade, crusher throughput, ag mills, Yeah, that's ones I can think of right now.
Yep, perfect. No, that's good. Thank you. Look, we're at 5 minutes to the hour, so I might just ask for some final thoughts. I do ask everyone, you're welcome to stick around and ask some more questions. Just like to keep it to a tight hour because I know people have meetings and so forth as well, but you are welcome to stick around. So I might ask any final thoughts, perhaps from you, Peter.
No, I think you've explained quite well the advantages. Machine learning has been tried and tested in a whole range of areas related to the mining industry, and so far everything looks as promised. We've had the exploration challenges here in South Australia. One of those that was identified in the machine learning challenge is now being drilled, so we'll know fairly soon how accurate it was. But it's been a long, slow process right back from the old neural networks nearly 25 years ago now up to this stage. And I was a skeptic from the start, mainly because neural networks were really just a statistical way of processing things in a slightly different way than we already did. But of course, it was a stepping stone to something now which is really starting to prove itself.
Yeah, it sounds like your training centre is quite the culmination of those stepping stones.
Yeah, if in the 16 projects, at least half of them have machine learning embedded into them. And we have the Australian Institute for Machine Learning as part of the university here, so they're contributing quite a bit to it as well. So it's a very interesting project.
Look, we'll watch it with close eyes as things develop as well. We did get some questions yesterday about information on it, and we'll make sure to circulate that as it comes to light. Orlando, what about you, mate? Any final thoughts? Anything you want to add?
Well, I think what's my view here? I think we, and I probably am talking about on behalf of all the mine engineers looking for optimizing value. I think we are quite boring so far, doing the same for many years, and we need a new challenge. And the new challenge coming from understand in much better way how the ore valley behave. And I think the big barrier to increase value today is to have a much better understanding of what we have in the ground and how the combination of attributes are combining to produce better output in the world sense, financially speaking, environmentally speaking, and efficient in efficiency type of speaking. So yeah, we need more input. We need better modeling.
Fantastic. And Penny, any final thoughts?
Just quickly, I've noticed something that Peter's been talking about, this interdisciplinary and the ARC, and it just made me think we've really got to get away from having conferences that are siloed. As PETRA, we really struggle to find a conference where we can present, because all the conferences that seem to be run globally all focus on either mining, metallurgy, or geology, and there's the complex ore body one was really good in that way. But I would love to see, and I don't know who's on the line here, but I'd just love to see some of the institutes put together interdisciplinary conferences so we can talk through some of the whole thing of value chain optimization.
I'd say we should do it, Penny, but I know you'll probably ask me to do all the work there. So
yes, maybe we should run our own conference to do interdisciplinary, or in collaboration with our partners at University of Adelaide.
Yeah.
Peter.
We're going to have great minds think alike. It's a good idea. Perfect, guys. That's an hour. Look, again, we do invite everyone to stick around. We've got another question or two come through from Jocelyn, and we'll be sure to answer that right away. I mean, that concludes the formal part of the proceeding, but do stick around. I wanted to ask Orlando about IES and CRC ore, and we didn't even get to that. So it was a really good conversation. I hope we'll definitely try and make the recording available, team. But do stick around. Thanks, everyone, for joining us. Thank you, Peter. Thank you, Orlando and Penny, for the discussion. I thought it was great. And have a wonderful day.
Thank you.
Thank you.
Thank you.